You can install every pressure switch, shutdown valve, gas detector, fire detector, and relief device shown on a standard drawing, and still end up with an unsafe facility, because a safety system is not a collection of devices. It is a chain of decisions that must detect failure, stop hazardous energy, control released inventory, and prevent escalation before the process crosses the point of no return. That is the real engineering challenge behind offshore surface safety systems. You do not begin with the instrument list. You begin with the failure. What can go wrong? What physical condition will reveal it? How early can you detect it? What source must be isolated? What happens upstream when you isolate it? What happens downstream? What protection remains if the first action fails? Can the complete function be tested after commissioning, after maintenance, and after years of process modifications? Those questions separate a safety philosophy from a crowded drawing. The main hazard is not pressure, level, temperature, or flow by themselves, because those are process variables. The real hazard is the chain that begins with an abnormal condition, develops into equipment failure or loss of containment, releases hydrocarbons, exposes people and equipment, finds an ignition source, and escalates into fire, explosion, pollution, or platform-wide shutdown. Your safety system must interrupt that chain at several points. First, prevent the abnormal condition from becoming a release. Second, if a release occurs, stop additional hydrocarbons from feeding it. Third, contain, drain, vent, disperse, or safely dispose of what has already escaped. Fourth, prevent ignition. Fifth, detect fire or hazardous gas quickly enough to force the facility toward a safer state. Sixth, prevent a local equipment failure from propagating across connected systems. This is why cause and effect logic matters. But the logic diagram alone is not enough. A high-pressure signal may be correctly programmed, but what does it physically shut? Does it close only the vessel inlet? Does it shut the producing well? Does it stop the upstream pump? Does it isolate the compressor? Does the closure create block discharge upstream? Does the process pressure rise faster than the shutdown valve can close? Does the relief system receive a new load? A signal is not safety. The final physical state is safety. One of the strongest design principles is the use of two protection levels that are independent of normal process control and, where practical, functionally different from one another. A pressure controller regulates normal operation. A high-pressure shutdown intervenes when control is no longer trustworthy. A pressure safety valve protects the equipment if the shutdown fails, responds too slowly, or cannot remove every pressure source. Those protections are not duplicates. They act differently. One removes the source, the other relieves the consequence. That is real defense in depth. Do not count layers by counting tags. Trace independence. Two pressure switches on the same impulse line can fail together. Two transmitters powered from the same vulnerable supply can fail together. Two shutdown valves controlled by the same solenoid can share one failure path. Two devices installed side by side can be lost in the same fire, impact, or corrosion event. Redundancy without independence is false confidence. Normal process control must also remain separate from safety thinking. A level controller is designed to maintain the operating level, but a high-level shutdown exists because the controller, transmitter, valve, actuator, utility supply, or operator intervention can fail. A pressure controller maintains process pressure, but a high-pressure trip exists because outlets can block, upstream conditions can change, control valves can fail, and downstream pressure can increase. A temperature controller regulates heat input, but a high-temperature shutdown exists because fuel systems, heat sources, and control logic can fail. The process control system keeps the plant running. The safety system stops the plant from becoming dangerous when control fails. Do not blur those roles. A disciplined analysis begins by defining each process component and its actual safety boundary. That boundary is not limited to the vessel shell, compressor casing, or pump body. It includes the connected inlet piping, outlet piping, valves, chokes, branches, and restrictions until another protected component takes over responsibility. This is where hidden gaps often appear. The vessel is protected, but the lower rated pipe between the vessel and the next isolation point is not. The compressor discharge is protected, but the cooler between the machine and relief connection has a lower design pressure. The pipeline is isolated, but a branch between the shutdown valve and check valve can still be backfed. The separator trips on high level, but the liquid already moving through the piping reaches the compressor scrubber before the valve fully closes. Safety boundaries must follow pressure, flow, inventory, and energy, not equipment tag numbers. For every component, identify the undesirable events. A pressure vessel can experience overpressure, underpressure, overflow, gas blow-by, leakage, and excessive temperature. A flow line can experience overpressure and leakage. A pump can experience blocked discharge overpressure, leakage, and reverse flow. A compressor can experience suction or discharge overpressure, low pressure, high discharge temperature, leakage, gas accumulation, and backflow. A heat exchanger can experience external blockage, thermal expansion, tube rupture, and cross pressure from the high pressure side to the low pressure side. A fired heater adds flame failure, excess fuel, low combustion air, low process flow, high stack temperature, and uncontrolled ignition sources. Once the undesirable event is clear, identify its causes and detectable symptoms. A blocked outlet creates high pressure. A vessel leak may create low pressure or low level. A failed level control loop may create high level and liquid carryover. Excess liquid withdrawal may create low level and gas blow-by. A heater with insufficient flow may develop high process temperature. A compressor valve failure may produce high discharge temperature. A gas leak inside an enclosure may not create a meaningful process pressure change, but it can create a dangerous atmospheric concentration. The device must be derived from the physical failure, not copied from habit. High pressure requires detection and source isolation, plus independent pressure relief where required. High level requires enough remaining vessel volume for detection, logic processing, valve movement, and continuing inflow before overflow occurs. Low level requires enough retained liquid between the trip point and outlet to prevent gas blow-by before shutdown is completed. These set points are dynamic. They are not decorative marks on a vessel drawing. A perfectly calibrated level switch at the wrong elevation is still failed protection. Gas blow-by shows why safety analysis must cross equipment boundaries. The separator may survive low level but high pressure gas can escape through the liquid outlet and overpressure downstream equipment designed for liquid service. The dangerous consequence occurs in another component. The low-level trip therefore protects the connected system, not just the separator. You must understand how much gas can pass, what downstream pressure can develop, whether restrictions limit the flow, and whether the downstream protection can respond in time. Protective shut-in should normally stop hazardous energy at its primary source. When a downstream vessel develops high pressure, closing only its inlet can create pressure escalation upstream. The header rises in pressure, then the flow line rises, then the well finally shuts. You have forced multiple components into abnormal conditions and depended on several extra safeguards. Where practical, shut the well, stop the pump, isolate the compressor, remove the fuel, or divert the heat source directly. There are valid cases where controlled cascading is operationally necessary, but that must be an engineered exception. Every intermediate component must be rated and protected for the transient. Every operating lineup must be considered. A shutdown philosophy that works only in the normal configuration is not complete. Overpressure protection demands particular discipline. A high-pressure shutdown attempts to stop the pressure source before the equipment limit is reached. A relief device protects against failure, delay, or unremoved pressure generation. Do not assume that fast valve closure automatically replaces mechanical relief. Shutdown valves can fail. Actuators can move slowly. Instrument gas can be lost. Impulse lines can plug. The pressure can rise faster than predicted. Thermal expansion can continue even after every process flow is isolated. Heat exchanger tube rupture can expose a low-pressure section to a high-pressure source. Fired equipment can continue adding heat. Relief capacity and discharge routing must address the actual governing scenarios. The same discipline applies to low pressure. Low pressure may indicate a major leak. It may also threaten vessel collapse. Atmospheric vessels can rupture under small positive pressure and collapse under vacuum. Blocked vents, thermal contraction, rapid withdrawal, and failed blanketing systems can create dangerous conditions. Atmospheric does not mean no pressure hazard. Leak protection also requires several detection layers because one device cannot detect every release. A large leak may cause a measurable pressure drop. A small gas leak may continue without changing process pressure but accumulate inside an enclosure. A small liquid leak may be masked by level control replacing the lost inventory. Low-pressure trips detect large leaks. Gas detectors detect accumulation. Containment systems collect liquids. Fire detection responds after ignition. Human observation detects conditions no single instrument was designed to interpret. Each layer has a defined detection envelope. Do not pretend that one instrument covers every leak size. Fired equipment requires even greater care because the process already contains an ignition source. You must manage process temperature, liquid level, circulation, combustion air, fuel pressure, flame proving, stack temperature, tube pressure, backflow, and safe startup sequencing. Flame failure must isolate fuel before unburned gas accumulates. Forced draft burners must prove airflow and blower operation. Low process flow through heated tubes can create rapid overheating before a remote temperature sensor responds. Startup procedures must ensure complete fuel shutoff, purge the firing chamber, limit trial for ignition time, prove the pilot, and require deliberate restart after flame failure. Many serious events begin during startup, relighting, shutdown, and return from maintenance, not during stable operation. The operating procedure is part of the safety system. Pumps and compressors must be analyzed by what they can physically generate. A positive displacement pump can continue increasing pressure against a blocked discharge until something fails. A centrifugal pump has limited shutoff head, but maximum discharge pressure must include maximum suction pressure, speed, and fluid density. A compressor package is not one black box. Suction, discharge, coolers, scrubbers, fuel, driver, enclosure, blowdown, and associated vessels each have distinct hazards. Package vendor protection does not remove the facility engineer's responsibility to integrate the package into the plant shutdown and relief philosophy. Pipelines require another level of thinking because the inventory beyond the platform can be enormous. An incoming pipeline can continue feeding the facility. A departing pipeline can backflow toward a rupture. A bidirectional pipeline cannot depend on a simple check valve. Shutdown valves must minimize exposed inventory. Check valves must minimize backflow where one-way flow exists. Remote sources and local actions must be coordinated. A pipeline is not just another process line, it is a stored energy system connected to your platform. Heat exchangers must be analyzed on both sides independently. The shell side and tube side can have different pressure ratings and different fluid hazards. A tube rupture can expose the low pressure side to the high pressure side. Relief capacity may therefore be governed by cross-flow through a failed tube, not by normal operating flow. Treat the dividing wall as a potential failed boundary. Gas detection, ventilation, and layout must also be designed as one problem. A detector cannot compensate for poor ventilation. A detector placed in clean incoming airflow may never see the gas accumulating behind congested equipment. A ventilation fan can spread gas across an ignition source. An enclosed module can convert a small release into an explosion hazard. The first line of defense is to prevent accumulation through open layout and effective ventilation. Detection then provides another layer. The detector response must also be rational. An alarm warns people. A higher concentration may trigger automatic isolation, but shutting everything can create new hazards. Stopping ventilation may worsen accumulation. Removing power may disable critical systems. Closing a valve may create upstream overpressure. The corrective action must reduce risk, not merely create activity. Emergency shutdown preserves the human ability to intervene when automation cannot understand the full event. People hear abnormal machinery, see smoke, recognize collision damage, and detect unusual combinations of symptoms. Emergency shutdown stations must be reachable during escape and must isolate hazardous production while preserving systems needed to manage the emergency. Fire detection must follow credible fire locations, not a neat drawing grid. Containment must direct liquid hydrocarbons towards safe drainage and collection. Sumps must be treated as hydrocarbon equipment, not forgotten utility pits. Drain systems must prevent gas migration. The final destination of every leak must not become the least protected part of the facility. The shutdown system is also only as reliable as its utilities. Pneumatic supply must be clean, dry, adequately sized, and capable of moving all required final elements during a major simultaneous demand. Tubing volume, restrictions, bleed rates, actuator size, valve friction, and line length all affect response time. You cannot prove pneumatic speed by looking at a schematic. You must calculate it, test it, or both. Fail-safe behavior must also be defined physically. Loss of utility should move each final element toward the safest achievable state. That does not mean every valve closes. Some valves must open for depressurization. Some systems must remain running for cooling, firewater, or emergency power. The safest position depends on the scenario. Testing completes the design. A safety function that is never tested is an assumption. Testing the sensor alone proves only the sensor. Testing the logic output proves only the logic. Testing the solenoid proves only the solenoid. The function is proven only when the initiating condition leads to the required final physical action. That means the shutdown valve moves, the source is isolated, the blowdown path opens where required, and the complete response time remains acceptable. Bypasses must be treated as temporary risk changes. Every bypass must be identified, time-limited, compensated, independently cleared, and visible to operations. A bypass is not merely a maintenance convenience. It is a deliberate degradation of protection. Design maintainability into the plant. Provide access, test connections, manifolds, calibration points, safe isolation, and practical removal space. A device that is difficult to test will eventually be tested less often. A detector requiring scaffolding for routine calibration will develop backlog. A level switch that can only be tested by upsetting the entire process will become operationally inconvenient. Poor maintainability becomes permanent risk. For lead engineers and project managers, the greatest failure is treating surface safety as an instrumentation package. Process defines the hazard and set point basis. Mechanical defines equipment limits. Piping defines isolation and relief connectivity. Electrical defines hazardous area compliance and power survivability. Layout defines ventilation, access, and dispersion. Operations defines real lineups. Maintenance defines testability. Instrumentation integrates detection and action. The lead engineer must force these disciplines into one coherent system. At every design review, ask direct questions. What can overpressure this equipment? What high-pressure source can reach this low-pressure section? What does this shutdown valve actually isolate? What backflow inventory does this check valve control? Where does the liquid go after high level? What downstream equipment is threatened by low level? What release is this gas detector expected to see? What fire location can this detector actually detect? What is the governing relief scenario? Where does the relieved material go? What happens upstream when this valve closes? What flare load appears when this system blows down? What position does every final element take when utility power is lost? Where is the equivalent protection when a device has been omitted? If the team cannot answer these questions clearly, the design is not finished. The strongest question is still the simplest. Show me what happens physically from the moment the failure begins until the facility reaches a safe state. Pressure rises, the sensor detects, the signal travels, the actuator vents, the valve moves. Inventory continues flowing. Upstream conditions change, downstream conditions change. Relief may activate, the source is isolated. Residual inventory remains, the process stabilizes. That complete sequence is the safety function. Design the process to be inherently safer before adding instrumentation. Identify the failure before selecting the device. Use independent protection where failure consequences are serious. Stop hazardous energy at its source. Do not create new hazards through shutdown action. Treat piping, backflow, and trapped inventory as part of the protected system. Design ventilation, detection, containment, isolation, and relief as one integrated architecture. Make every safeguard testable. Document why every device exists and why every expected device has been removed. Revalidate the safety logic whenever the process changes. A safe offshore facility is not created by installing more hardware. It is created by understanding how the process can fail, detecting that failure early, stopping the energy that drives it, preventing escalation when the first defense fails, and proving throughout the facility life that every protection layer can still perform its intended function. Share your experience in the comments. Where have you seen a safety system look correct on paper, but fail during commissioning, operation, or testing? Which design assumption creates the most hidden risk? Do we sometimes over-instrument facilities while under-analyzing the real failure path? Leave your views, technical lessons, and practical examples, because engineering improves when experience is shared rather than buried inside project files. Like this episode, share it with engineers who design, review, operate, or maintain process facilities. Subscribe to the channel for more practical engineering and project management discussions. And follow my LinkedIn newsletter for deeper guidance on engineering design, safety systems, management principles, and real project execution.